Hi, my name is Bailey Chapin, and this is my Physics 2212 Lab 3 bar magnets. First, let's get into the purpose of the lab. The purpose of the lab is to investigate how distance affects magnetic fields of a bar magnet. We will use the Biot-Savart law to measure magnetic fields both on and off axis. We will then use GlowScript to model magnetic fields of a bar magnet and then compare the experimental and computational model. I want to give a brief preview of the experimental findings of the lab. The magnitude of the net magnetic field increased as the distance between the magnetometer and the magnet decreased. The magnetic dipole moment was found to be 18.84 amperes square meters. The measured off-axis magnitude of the magnetic field was 3.58 times 10 to the negative 5 teslas, and the simulated or computational model of the off-axis magnitude of the magnetic field was found to be 2.03 times 10 to the negative 6 teslas. The main fundamental physics principle of this lab is the Biot-Savart law, which states that the magnetic field in teslas due to a small current element at any point is related to the distance between the source and observation point as well as the current represented by the variable I. The Biot-Savart law equation is shown below, and then the magnitude of the magnetic field for both the dipole on axis and off axis, where R is much greater than the distance between the positive and negative charge of the dipole, are shown below as well. Another note is that the direction of the on-axis magnetic field is the same direction as the magnetic dipole moment, whereas the direction for the off-axis is opposite of the direction of the magnetic dipole moment. These equations here are more physics principles that apply specifically to this lab. In the equation here to the top left, the magnitude of B bar is equal to K times R to the N, where K is a combination of constants and parameters and N should be negative. This is the equation for the distance dependence of the magnetic field in this lab. The equation to the right is the linearization equation to find the dipole moment, which will be explained later. The last equation below is the off-axis magnetic code, the magnetic equation that will be put into the code for the computational model. Just a few other notes in the introduction. The system here is the magnetometer of the phone, and the surroundings are the bar magnet, or specifically the magnetic field that comes from the bar magnet. It is important to note that we are assuming that the field of the bar magnet is to be treated as a magnetic dipole for this experiment. Here is an abbreviated procedure of the experimental model. You will need a small bar magnet, a magnetometer app, a meter stick, and some tape. You will orient the phone such that the app has an x component of 0 to compensate for magnetic north, which is the initial condition. You will measure the distance between the magnet and the phone so that the magnetometer is on axis to the dipole of the magnet at the following x components listed here. You will make 3 measurements of each. You will then measure the distance between the magnet and the magnetometer so that the magnitude of the net magnetic field is 100 teslas. You will record this y component of the Earth's magnetic field and then apply this distance in the y direction to form a 45-degree angle and measure the magnetic field 3 times. And there's a picture of this on this slide as well. Here is the results of the experimental data and some key observations as well. The further that the magnet is, the lower the magnetic field is in the x direction, and then the closer the magnet is, the greater the magnetic field of the x component. The next step is to solve for the magnetic dipole moment using the equations from the fundamental physics principles at the beginning of the presentation. You will apply this equation above to the equation that was found on your experimental results data sheet, where the slope of the line from the data sheet is n and the y-intercept is equal to natural log of k. By setting the magnitude of B bar equation to the magnitude of the magnetic field of the dipole on axis, you can solve for mu, or the magnetic dipole moment, using this equation to the right. Let's get into the computational model. Here is the code for the constants, initial conditions, and magnetic field. Note that we inputted the magnetic dipole moment from the experimental results here as 18.84, as well as the off-axis equation for the magnetic field down below. Here is the code for the part of the computational model that makes the arrows of the magnetic field. Finally, this is the part of the computational model where we visualize the 45-degree off-axis of the magnetic field and add an arrow as well. Computational model results. The orange arrows are the on-axis, and they go in the same direction of the magnetic dipole moment. The blue arrows are off-axis and go in the opposite direction, and the arrow here for the magnetic field of the 45-degree is too far away to be seen on the visual model. Now we can compare. The magnetic dipole moment for both models was 18.84 amperes meters squared. The experimental off-axis magnetic field ended up being 18 times larger than that of the simulated magnetic field. This is a pretty big discrepancy, so some possible sources of error are the measurement error of the lengths between the magnet and the magnetometer, or the magnetometer readings. There could have been the presence of other magnetic fields, there could have been movement of the phone, or even rounding or calculation errors. If we had not compensated for the magnetic north and used some other intermediate angle, both the x and y components would have been different if the magnetic north was not accounted for. The z component would stay the same because the magnetometer was laid on a flat surface, and it would still be 0 as the magnetic field would lie in the same plane as the phone screen. If we stuck two identical magnets together, based on the principles of superposition, the magnitude of the magnetic field would not only increase but would be approximately double the magnetic field of one magnet. The distances measured at the different t values would also be decreased due to the relationship found in this lab. Thank you.